Hello and welcome to our lesson on graphs of polynomial functions. So just to continue our discussion of polynomials, we, again, for calculus purposes, need to be able to have a visual in our head when we see the equation of a polynomial function. What are the end behaviors doing? Where is it going to be crossing the x-axis? Where is it going to cross the y-axis? What are the turning points going to look like? All these things have to come together. So far, we have talked about end behaviors. We know that if the degree of a polynomial function is even, that both ends are going to go up toward positive infinity. Both ends rise, excuse me, or go up toward positive infinity. So think about like y equals x squared, or x to the fourth, or x to the sixth. All of them sort of look like this. Again, both ends go up. If the degree of a polynomial function is odd, then the left end falls toward negative infinity while the right end rises toward infinity. So like a cubic function, y equals x to the third or x to the fifth or even x to the first, they all do the same thing in terms of end behaviors. The left end falls, the right end rises. Unless, of course, we have a negative leading coefficient. A negative leading coefficient would reflect the graph over the x-axis, and that would reverse those end behaviors. Okay, but it will always be true that if we have a polynomial function of even degree, the end behaviors match. And if we have a polynomial function with an odd degree, then the end behaviors will be opposite one another. Okay, so that's not new. We've also discussed turning points as either maximum or minimum vertices on a polynomial, on the graph of a polynomial function. And in particular, we are going to call that turning point or vertex a maximum if the graph is changing from increasing to decreasing. So a maximum vertex or turning point might look something like this. Or again, the graph is increasing till it gets to that turning point, and then it is decreasing. And vice versa, if we change from decreasing to increasing, then that turning point or vertex would be a minimum. So at a minimum, we're going to still turn, but from decreasing to increasing, so something like this. So our turning point would be here. Again, we are increasing and decreasing. So increasing till we get to the turning point, and then decreasing means it's got to be a maximum. And if we are decreasing and then we get to the turning point, turn to increasing, then that turning point has to be a minimum. Okay? Not new. Now, you may or may not have learned this in college algebra, but there is a rule when it pertaining to the number of turning points that can exist in our polynomial function. So a polynomial function of degree n has at most n minus 1 turning points, and there's got to be at least one turning point between successive zeros. So let me just show you for a second, maybe here. If, for example, we had a cubic function of some sort, okay, that means we have a degree of 3, then graphically, the maximum number of times a cubic function can touch the x-axis would be 3. Degree of 3 means it could have 3 factors, and there could be 3 real solutions to the equation or x-intercepts for the function. So if we touch the x-axis 3 times, and let's just pick those 3 random spots, or any 3 spots, it wouldn't really matter. Now, degree of 3, I know that on one end of the graph, my graph is going to, or on the left end of the graph, my y values will fall toward negative infinity, and on the right end of the graph, they're going to rise toward positive infinity. Now, if in between the two x-intercepts that I have here, I have to pass through a maximum of one more, then I have to turn my graph at some point to get back down to this one, and I would have to turn again to get back up to this one. So what we see when we have our maximum 3 x-intercepts and our appropriate end behavior, that this graph has 2 turning points. And since that's the maximum number of x-intercepts, that is the maximum number of turning points. And I can continue this. So like, let's say we had a degree of 4. If we had a degree of 4, then again, imagine crossing your x-axis 1, 2, let's say 3, 4 times, wherever, but let's just say these 4. Now, degree of 4, our ends are going to be both going up toward infinity. Now, again, to get through the other two x-intercepts, I would have to turn, come back up to get this one, turn again to come back down through this one, turn again to get here. So with that maximum number of x-intercepts, I can see 1, 2, 3 turns. Okay, so the number of turns, maximum number of turns, will be 1 less than the degree. That doesn't mean it has to do that. So like our parent cubic function with the 1 inflection point and no turning points, right? We can have a degree of 3 and 0 turning points, but the maximum number of turning points is 1 less than that degree. Okay, so that's a rule we want to keep in mind. Now, intercepts. I know we've talked about intercepts before. We just want to add a little to it. So we know that at a y-intercept, if we're crossing the y-axis, our x value has to be 0, and vice versa at an x-intercept, that our function value y has to be 0. And we talked a lot in the previous topic about x-intercepts and ways to find them. The x-intercepts of the graph also represent the zeros for the function, right? Those are the x values. We could plug into 0 out the function value. They also represent the real roots or solutions to the related equation. Now, we saw at the end of the previous topic how if we were solving, let's say, a cubic equation that only had one real solution, that one real solution was going to show up graphically for us. The two imaginaries didn't. So the imaginary solutions that don't show up for us graphically, we do have to remember they come in pairs. Imaginary solutions have to come in pairs, and that should make sense. When we end up with an imaginary, we end up with a negative under the radical, let's say negative 36, for example, and that's always part of, you took the square. Let me back up a little bit here. Let me actually go to my scratch paper. If you're looking at imaginary solutions, you have a couple ways to come up with them. So let's say you're solving like this: x squared equals a negative 36. Well, you would take the square root of both sides to solve, and every time you take the square root, you introduce the plus or minus, because a positive and negative squared are going to produce that same result, and you get your 6i. So those imaginaries, again, coming in pairs. Or it comes from the quadratic formula. Suppose you had like negative 2 plus or minus the square root of your negative radical 36 over 4, something like this. Again, that plus or minus component will be connected to that square root of that negative. So anytime you have imaginaries, they come in pairs. So having only one imaginary solution, not an option. You have to have an even number of imaginary solutions. Okay, again, something important to keep in mind. So the real solutions to our equation, those do translate into x-intercepts. The imaginary solutions to our equations, they do not translate into x-intercepts. They cannot be found graphically. And then also, if I need to know the total number of solutions, that's indicated by the degree. I put the wrong word here. The degree of our polynomial tells us the total number of solutions that are going to be possible. But remember, those are complex solutions. So for instance, looking at this first box, I put a cubic function in here. So we've got a degree of 3. That degree tells me that I should have 3 total solutions. But when I look at the graph, it only touches the x-axis one time. So of the 3 complex solutions that exist, only one of them is real, which means the 2 remaining have to be imaginary. Okay. Looking at g of x, again, we have this degree of 4. That means there should be 4 total complex solutions. But this graph never touches the x-axis. So none of those roots or solutions are real, which means all 4 of them would have to be imaginary. Or looking at y equals 4x to the 4th minus 3x squared minus 1. Again, degree of 4 means I should have 4 total solutions. And I see this function cross the x-axis 2 times. That means 2 of my solutions are real, and the other 2 remaining solutions have to be imaginary. Okay, so that's sort of the concept. Again, we want to familiarize ourselves with. Hopefully that's kind of review from college algebra. But there's another little detail, and it's relating to what we call the multiplicity of our solution, or the multiplicity of our roots. And let me show you, back to my scratch paper real quick. Okay, so consider this function here, y equals x to the third minus 2x squared minus 7x minus 4. If I graph this function, we see it touched the x-axis a couple times. So we got an x-intercept there at 4, and we have an x-intercept there at -1. Now, does that mean that those are the two real solutions and there would be one remaining imaginary solution because there should be 3 total? Well, that's not a possibility. Remember, the imaginaries have to come in pairs. So what's going on with this function is one of the x-intercepts, one of the roots, the zeros, the solutions, has a multiplicity other than 1. Now, if you're familiar with the words, and you probably already know where I'm going, if not, then just go with me for a second. So we know from our graph that -1 is a solution, which means x plus 1 would have to be a factor. So what I'm going to do is take the polynomial that I have here, and I'm going to divide that factor out. So I'm going to use synthetic division, put my -1, my 0 outside of the box, and then 1, -2, -7, -4 inside the box. Bring this down, multiply, I get -1, add, I get -3, multiply, I get 3, add, I get -4, multiply, I get 4, add, I get 0. Good, got a 0. So I started with this cubic polynomial. I divided it down to now I have a quadratic, but I have another factor here, right? My graph also touches the x-axis at 4, so if x equals 4 is a solution, that means x minus 4 has to be a factor. So now I'm going to take this polynomial and divide out that second factor. So if I divide by 4, when I bring this down, 4 times 1 is 4, add here I get positive 1, multiply I get 4, and there's my 0. So this is the third factor of my function. Again, I started with an x cubed, got down to an x squared, and now I have an x to the first and a constant of 1, another factor of my equation. So on the graph, again, I had this x plus 1, and I had this x minus 4, and now I just divided down to figure out that this is what's left over. It's another factor of x plus 1. So what we're seeing is one of our solutions repeats. It has a multiplicity of 2. It repeats twice. So in other words, I could say this is x plus 1 squared times x minus 4. This would be the factored form for that function. So the fact that this factor happens twice, or our solution of -1 happens twice, is why at that root we see that quadratic behavior, right? And the fact that this root over here happens once is why at this root we see linear behavior. And in fact, whatever the multiplicity is dictates that behavior. So if I had a root like, let's say, x minus 7, and it was cubed, then that solution happening 3 times means at that x-intercept we should see cubic behavior. So let me just show you. X minus 7 to the, oops, I said 7. 7 to the third power exponent. There we go. And over here at 7, there's that cubic behavior at that x-intercept. Again, let me make this a 2. There's quadratic behavior at that intercept. Let me make this a 5. There's fifth degree behavior at that x-intercept. Let me keep it as a 1. There's linear behavior at that x-intercept. So when we're seeing the behavior of our graph at the x-axis, at the x-intercept, we can tell its multiplicity, or at least something about it. So if the graph goes straight through, it's got to be linear. That solution has to happen once, which means then that factor is a factor of our polynomial just once. If it looks like a parabola, we can at least assume that the multiplicity is even. And if it looks like an inflection point where it kind of wiggles through instead of going straight through, then we can assume that it's an odd and it's bigger than 1, because linear would have to go straight through. Okay, so let's go back here. Again, the multiplicity, I'm so sorry, the multiplicity of the root, or the x-intercept, dictates the behavior. And what happened to my pen? It dictates the behavior of our graph at that x-intercept. So for example, f of x equals x minus 5. I know that's my parent linear function, and it's just shifted to the right 5. So if I just shift it to the right 5, there it is. But again, if I look at the root at 5, it goes straight through its linear behavior at that root. Now g of x equals x minus 5 squared. That's my parent parabola shifted to the right 5. And again, if I shift over to the right 5, my parabola, I can see at that x-intercept of 5 again, I have quadratic behavior. And then in the next one, I have my x to the 5th to the 3rd power. So if I shift over my cubic function to the right 5, then I'm going to have an, oops, let me go back to blue. I'm going to have an inflection point at the root. So the x-intercept right here, again, it's cubic behavior. And if I looked at x minus 5 to the 4th power, that's going to be a slightly wider parabola, still shifted over to the right 5. And again, at the x-intercept, I have that 4th degree behavior. So the multiplicity of the root indicates the behavior at the x-axis. Okay? So, using all of this knowledge, the multiplicity of the roots, the end behaviors, the number of turning points, all these things, y-intercepts, x-intercepts, we should be able to get a pretty good sketch of a graph, especially if it's in factored form, just using that knowledge and not having to use any technology. Okay, so for example, if I'm looking at problem number 1 here, if I want to sketch the graph of f of x, which is a skill you should have, first, what's the degree? The degree for this function, the number of variable factors, if I was to multiply x and x and x, I'm going to end up with x to the 3rd power. So if this has a degree of 3, that would tell me my left end would fall, my right end would rise. However, I have a negative here, so we have a negative leading coefficient, which means instead of the left end falling and the right end rising, those end behaviors are reversed. So the right end is going to fall, and the left end is going to rise. So a negative leading coefficient. These two things tell me that basically the ends will look like this. The left end's going to go up and the right end's going to go down. Now I can also, because of these factors, see where I'm going to cross the x-axis. So I'm going to have x-intercepts at x equals -1 and +2 and +4. And if I wanted to find a y-intercept, it's not so bad. A y-intercept we know is where x is equal to 0. So if I input a 0 for all of those x's, if I find f of 0, then -3 times 0 plus 1 times 0 minus 2 times 0 minus 4 means I'm just looking at -3 times 1 times -2 times 4. So -3 times 1 times -2 times -4. So that's going to be 3 negatives, which will make a negative, and 3 times 2 is 6, 6 times 4 is 24. So -24 is where this thing is going to cross the y-axis. -24, 0, comma, -24. So this equals -24, but that's my y-intercept, the coordinates there. And I could just say y equals -24 as well. Okay, so degree of 3, negative leading coefficient, maximum of 2 turning points, and let's try to sketch. So I'm going to start by graphing the x-intercepts. So let's see. Let's go -1 and then 1, 2, 3, 4. And then the y-axis, I got to get up or down to -24. So let's just go 10, 20, 30. And this is just a sketch, so you can kind of make it work for you, which is exactly what I'm going to do. All right, so let me plot the points I got here. I know I'm going to cross the x-axis at -1, at +2, at +4, and I'm also going to cross the y-axis at -24, which would be like down here somewhere. Okay, and I know my end behaviors. I know the left end is going to go up and the right end is going to go down. And what I want to do is sketch those end behaviors from my leftmost and rightmost x-intercepts. So I'm going to go to the left x-intercept, leftmost x-intercept here, and say, okay, my graph has got to go up on this end, and then go to my right end and say, okay, this end's got to go down. So something like this. And then the rest of it sort of makes sense. I'm going to have to be decreasing and get through this route, and at some point, I don't know exactly where, it could be over here, um, but at some point I'm going to have to turn to come back up and get through this x-intercept, and then again at some point I'm going to have to turn to come back down to get through this x-intercept. So this would be a pretty reasonable sketch for f of x. If we really wanted to know how far up that point was going to go and how far down this point was going to go, we could make a table of values. Maybe I input -3 and see how high, or sorry, I could maybe input +3 and see what my output is, and I could maybe input a +1 and see how low my output is. But if we're just trying to sketch, this would be good enough for me. And in fact, let's go ahead and just check. Let's see how close we got. And I need my function. So a -3, and then we have an x plus 1, and then an x minus 2, and then an x minus 4, and nothing. Okay, so here we go. And let me zoom how my, oops, gosh, how it's kind of zoomed on my paper, and that's pretty close to what we did. Okay, so basically we captured the behavior without having to go to the technology. We just used it to confirm what we did. Okay, so let's try it again, and if you're feeling good about this, pause the video and give it a shot. If not, totally cool. So this one is going to have a degree of, we got 1, and then there's 2 factors of x here, so that's 2, 3, and then there's 3 factors of x here. So 3, 4, 5, 6 altogether factors of x, variable factors of x. That's going to be a degree of 6. And my end behaviors are going to have to match. And the leading coefficient is positive, so positive leading coefficient. This tells me my ends have to do this. They both ends have to go up. And x-intercepts, I can see from my factors, one of my x-intercepts, so let me use my highlighter again, just to be consistent. I'm going to get one here, going to get one here, going to get one here. But this time, we have multiplicities other than 1. So each of the factors in the previous problem happens one time. So I went straight through each of those routes. But here, I have, this x-intercept's fine. So I'm going to have an x-intercept at 0, and that's got a multiplicity of 1. It's going to go straight through like we would expect. Now, at x equals -5, we have a multiplicity of 2. This route at -5, this x-intercept, should look like a parabola. And then at x equals +1, we have a multiplicity of 3. So at this route, we should look like a cubic function. We should have an inflection point there. Okay, and then we have a y-intercept that we're going to find by inputting a 0 for x. Now, if I put a 0 for x, a 0 here is going to make everything 0 out, so it's going to cross at 0, 0, which makes sense because we already have that point here. And we can't have more than one y-intercept for our polynomial, otherwise it wouldn't be a function. So let's put it all together. And okay, so we're going to cross at 0, at -5, and at +1. So 1, 2, 3, 4, 5, and 1. So something like this. And again, crossing at, or yeah, going to have a point at 0, going to have a point at 1, going to have a point at -5, so out here. And I know my ends are both going to go up, so from the leftmost I'm going to be going up, from the rightmost I'm going to be going up. It's in between. Now, this is going to be a maximum of degree of 6, 5 turning points. I don't know that all that's going to happen in here. Let's see. So at -5, we have a multiplicity of 2, which means at this x-intercept here at -5, we actually should see our graph bounce. And over here at 0, we're going to go straight through. And so if this thing has to bounce, has to look like a parabola here, we got to come up. And then at some point, I don't know where, but we're going to have to come back down to go through this x-intercept. So I don't know exactly how that's going to look or what the width of this bounce is going to look like. Oh my gosh. But it pen. Sorry. It does have to hit the x-intercept and come back up. So again, right there, we have to look quadratic. And again, it's going to have to turn somewhere. and pass through this intercept through it, not straight through. It's got to be linear there because that's got a multiplicity of 1. And then I'm going to have to make this turn a little bit more. Okay, so I need to give myself more space. I need to come down, and then when I come back up at some point, again, I'm going to have to inflect here, which makes this really look bad. I need to stretch this out. I don't give myself enough space. So let's just say that's positive 1. Okay, so again, I'm bouncing here, and then I gotta come back through and go straight through this one, linear behavior there, and then I'm gonna have to turn again and have an inflection point here, so something like this. Okay, so now that we've straightened this out, and it may take you a few attempts, and remember, this is just a sketch, so I see a couple different turning points in there, at least 1, 2, 3 turning points. Possible there are more, but what we've captured is the end behaviors. We've captured the roots with their multiplicities, and the y-intercept. So let's go ahead and look at this just for fun. This might not be exactly right, but the main features should be captured. And I need my equation. So I got an x, and I got an x plus 5 squared outside of the... My goodness, fat fingers really have a tough time here. And then an x minus 1 to the 3rd power. Oh, look at that. Looks strange, just like mine did, okay? So the same sort of basic behaviors. Now, I didn't make my graph go nearly as high as it needed to, but you can see that the left and right end both going up. You can kind of see the weirdness that I have here in quadrant 4. That weirdness is happening there as well. There's an inflection point at 1. We're going straight through the origin there. There's that quadratic behavior over here. I gotta zoom. Oh my gosh. Work with me, calculator. Try this again. Okay. Come on. Not really sure why. Anyways, maybe you can see it already. There's, again, the quadratic behavior at -5. The only thing I didn't really capture well is here, my turning point. Again, if we really wanted to, we could pick a couple of these inputs, plug them in to the function, and see how high the outputs should be if we wanted to get a better representation, but I think this sketch is decent enough, and that's all we're trying to do is sketch. So I can see this graph goes like way up here to 800. The only way to know that is to plug something in, which we could do, but again, the basic idea is good enough. Okay, so now I want to show you one more problem. We're going to go in reverse. If I give you the graph, you should be able to read some similar information and maybe come up with an equation. So if I say, here's the equation, make the graph, here's the graph, make the equation. So let's look at it. First, we're writing a polynomial function of least possible degree that has the characteristics that we see in this graph. So we have here an x-intercept at -3. So if x is equal to -3, we have an x-intercept at -3, then I know that x plus 3 is going to be a factor. And I know it's going to be a factor one time because that graph goes straight through. It has linear behavior there at that x-intercept. Now over here at x equals 1, again, I know that x minus 1 is going to be a factor, and that is more quadratic behavior. Now, all we're really guaranteed is that it's even. It's probably quadratic, but the only guarantee is it's even. Now, because this says least possible degree, we're going to stick with the least possible even, which would be 2. So those are all the roots that I can see. Those are the only factors that I can actually write for my function. The other piece we have to account for is the y-intercept. So right now, and don't write this if you're taking notes, okay? Right now I could say my function, let's just call it f of x because it hasn't been named here, has a factor of x plus 3 and it has a factor of x minus 1 squared. If I input a 0 for x, so a 0 for x, to find my y-intercept, then I would be left with 3 here, and I would be left with -1 squared here, which would be 1, and that would be 3, and that's not the y-intercept that I see in my picture. It just means there's some coefficient that isn't accounted for. So when we're writing our function, there's some I need another color. When I go to write my function, there's going to be some coefficient here. I'll just call it a. That's multiplied by our factors, so our x plus 3 and our x minus 1 squared, and I want to figure out what that is. So again, I want to input my x value of 0, but also input my y value of 6 and figure out exactly what a is supposed to be. So I'm going to input my x value of 0, input my y value of 6. So y is going to go over here for f of x, and again, I'm going to try to figure out what a is. And then I'm going to have my plus 3 here, my minus 1 here, my square here. I'm going to input my value of 0 for x. And this will allow me to, by inputting that point, figure out what that coefficient is that we didn't account for. So I have, again, 6 on this side. We've already established that 3 times the positive 1 here is going to be 3 times a, which means that coefficient should be 6 divided by 3, which is 2. So my function is actually going to be, let's see, can I fit all this here? Why is my pen is not, there we go, not cooperating. Sorry, lost the word for a second. Okay, so now we're going to say our function f of x is 2 times x plus 3 times x minus 1 squared. So this used to be the polynomial function of least degree that has the characteristics that we see in that graph, meaning it should have a y-intercept at 6, which it does. We've already guaranteed if I input a 0, I get a 6 for y. Crosses the x-axis at -3 and at +1, and when it crosses at -3, it goes straight through. When it hits at +1, it has that quadratic behavior. And in fact, again, we could verify our work with our calculator. So 2 times x plus 3 squared times x minus 1. Oh, no, that wasn't squared. What am I doing? Sorry, it's just too late at night. Get rid of that. This one is the one that's squared, and let's zoom, and there we go. Picture that looks, yeah, like what we did. So I see the same behavior at this x-intercept, same x behavior at this intercept, and same y-intercept as what is on my paper. So we did it. Okay, so we got to be able to go both directions. If here's our function in factored form, let's sketch a picture. If I give you the picture, you should also be able to give me the function in factored form. And yes, this is factored form. If I wanted the standard form, then we would take that and multiply it out. But the standard form, not as useful, does not show us as much information, so factored is preferred if we can get that. Okay, so that's it. I hope you have enough to go off of for your assignment, but as always, if you need any extra help, then just reach out. Till next time, take care.